Calculus Video 8, Examples using the power rule. Alright, so let's recall the power rule says that if I have a function f of x equal to x to the n, the derivative of that function is n times x to the n minus 1. That is the power rule. Alright, so what that means is, for my first example, I have a function f of x is equal to x to the fifth. The derivative of that function, the exponent here is 5. The 5 is like my n value. So I'll have an n value of 5 as a coefficient. And then it's x to the 5 minus 1. Or 4. Therefore, 5x to the fourth. And you're done. But let's remember what this means. This is the derivative function. This is a function, 5x to the fourth is a function that gives the slope of any tangent line at any point x on the curve x to the fifth. Right, so x to the fifth is a curve. You pick any point on x to the fifth. You plug the x value of that point into 5x to the fourth, and you get the slope of the tangent line at that point. I think that's pretty cool. Example 2. F of x is equal to 3x to the fourth. This time we have a coefficient out in front of the x to the fourth power, so 3x to the fourth. The n value is 4. What we want to do here when we find the derivative of f of x, f prime of x, is we're just going to leave that 3 multiplied by whatever we get when we use the power rule. So it's 3 times whatever the power rule gives us, the x to the fourth part. So the n value is 4, so we'll have a 4 as a coefficient, times x to the n minus 1, that would be 4 minus 1. So we have 3 times 4x to the third, or simply 12x to the third. That is the derivative function for 3x to the fourth. Again, it's the function that tells us the slope of the tangent line at any point, any x value on the curve 3x to the fourth. And now you can see why the power rule is so useful. This is much faster than trying to do this. F prime of x equal the limit as h goes to 0 of 3 times x plus h to the fourth minus 3x to the fourth over h. Well, that part's not too bad. X plus h to the fourth can take a little bit, right? If we have Pascal's triangle, it's maybe not quite as hard, but it's going to take a little bit to do x plus h to the fourth. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So those will be the coefficients of x plus h to the fourth, of the x to the fourth, plus 4x to the third h, plus 6x squared h squared, plus 4x h to the third, plus h to the fourth. All of that then multiplied by 3 to give us 3 times x plus h to the fourth. Almost running into my next problem here. I won't finish this one out, but it's the limit as h goes to 0 of 3 times x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth, all minus 3x to the fourth over h, and you multiply and you cancel, and then you divide by the h, and then you let h go to 0, and you get your answer. Notice the answer is going to come solely from this 3 times the second term, 4x to the third. 3 times 4x to the third is 12x to the third. Point there being, the power rule is much more efficient than the limit definition of the derivative. Okay. The great thing about the power rule is so far we've only done this with one term, 3x to the fourth or x to the fifth, but it can be done for polynomials that are connected by plus and minus. So basically what we're doing is we're doing power rule in this next case 4 times. We're doing the power rule on 1/2 x to the fourth, the power rule on negative 3x to the third, the power rule on 1/6x squared, and the power rule on negative 2x. And we get this. F prime of x is equal to 1/2 times 4x to the third, right? The n value is 4, that comes down as a coefficient, and you subtract 1 from the exponent. Minus 3 times 3x squared. Again, the 3 exponent comes down as a coefficient, and instead of an exponent of 3, we now have an exponent of 2. We subtract 1 from the exponent. Plus 1/6, 2x to the first. Minus 2. Okay, let's talk about this one. This exponent here is 1, so I get a 1 here, and then it's x to the 1 minus 1 is 0. But what is anything to the 0 power? Except for maybe 0 or infinity, x to the 0, anything to the 0 is just 1. So that's just x to the 0 is 1 here, and we get an answer of 1/2 times 4 is 2, 2x cubed minus 9x squared plus 1/3 x minus 2. And eventually you just do this pretty fast, and you don't even need that in-between step that I wrote there. You're thinking about it like this. 4 comes down as a coefficient. 4 times 1/2 is 2 times x to the third. Second term, the exponent of 3. 3 times 3 is 9 times x squared, right? And you can just kind of do this in your head as you go along and get more proficient at this. We had an example where we did the limit definition of f of x is equal to, I think we had square root of x plus 1 or square root of x minus 3. I can't remember which one. But in this case, I'm just going to leave it f of x equals the square root of x. And you might be saying, I don't see the power. Where's the exponent here? And we have to remember that a square root has an index of 2 right here, right? That the square root of x can be rewritten as a rational exponent, x to the 1/2. Now, I haven't shown this with the binomial theorem with fractions as exponents, but it turns out it works still. The power rule still works with fractions as exponents. It's great like this. So remember the power rule. If f of x is x to some power n, the derivative is n times x to the n minus 1. So when we do our exponent, we're going to be subtracting 1 from the exponent. We'll be subtracting 1 from fractions, but that's okay. We can do that. F prime of x here is, we had an exponent, an n value of 1/2. That then becomes the coefficient of 1/2. X to the 1/2 minus 1. Well, 1/2 minus 1 is negative 1/2. And this, by the way, is a fine answer. Box, feel good. But what does this mean? Remember, a negative exponent means you reciprocate it. Kind of side work over here. X to the negative third is the same thing as 1 over x to the third. This is sort of just kind of recall. An x to the negative 1/2, that's the same thing as 1 over, the 2 stays in the denominator, x to the positive 1/2. But we also know a 1/2 power is the same thing as a square root. And we get this, 1 over 2 root x. Either one of these mean the same thing, are fine, just depends on the context of which one you want to use. Okay, what if I have, 3 times the 4th root of x? All right, that's the same thing as, let's rewrite that, 3 times x to what power? Well, this is an exponent of 1 in here, an index of 4, so that's x to the 1/4. So when we find the derivative, f prime of x, that's 3 times 1/4, the exponent comes as a coefficient, x to the 1/4 minus 1. All right, 3 times a 4th, that's 3/4. X to the 1/4 minus 1 is negative 3/4. Again, perfectly happy with that answer. 3/4 x to the negative 3/4 is fine. But we should also know that's the same thing as 3 over the 4th root of x to the 3/4, which is the same thing as 3 over the 4th root of, 3 over 4 times the 4th root of x cubed. Try that again. 3 over 4 times the 4th root of x cubed. Maybe you look at it like that. We need to, either form is fine with me, but we need to be able to convert back and forth between the two forms. Okay, how about a function like 2 times the 5th root of x cubed? Well, first we rewrite 2 times x to the 3/5. The derivative, f prime of x, hopefully you're getting pretty good at these by now, that's equal to 2 times 3/5 x to the 3/5 minus 1. That is 2 times 3/5 is 6/5. X to the 3/5 minus 1 is negative 2/5. Again, fine answer. Or rewrite it as 6 over 5 times the 5th root of x squared. Okay, very good. Let's keep going. All right, one of the problems we had was 1 over x, or I think it was 1 over x minus 3. Again, before you take the derivative here, what you want to do is rewrite that, in this case, x to the negative 1. It's kind of like the opposite of what we did back up here, where we had x to the negative 3rd. Let's write this right here. X to the negative 3rd is equal to 1 over x to the 3rd. We could take 1 over x to the 3rd and rewrite that as x to the negative 3rd. So 1 over x, same thing as x to the negative 1. And now we just take the derivative. Our n value here is negative 1. So f prime of x is equal to negative 1 times x to the negative 1 minus 1. That's negative x to the negative 2. Good answer. Or negative 1 over x squared. Okay. How about the function 3 over x squared? Well, rewrite 3x to the negative 2. F prime of x, bring that negative 2 down, that's 3 times negative 2, x to the negative 2 minus 1. That is negative 6, 3 times negative 2 is negative 6, x to the negative 3rd. All right, and finally, what if the n value is 0? If you remember when we started this power rule, we said that the n value cannot be 0. So something weird is going to have to happen here. Well, maybe I slightly misspoke there. We'll keep going. F of x, it's not that it can't be 0. It's that the power rule kind of is a little bit different, but we'll go through it. F of x is equal to 3x to the 0. If I do the power rule, f prime of x is equal to 3 times 0, x to the 0 minus 1. Is equal to 3 times 0 is 0, x to the negative 1, or 0 over x, which is just 0, less x is 0, and so we have that whole thing. So power rule is a little bit weird here. Instead, think about it like this. We don't really think 3x to the 0, because 3x to the 0, x to the 0 is just 1, so we just really think of that as 3. What is the derivative of 3? What is the slope of the tangent line for the function f of x equals 3? And instead of f of x equals 3, think about y equals 3. F of x equals 3, y equals 3, same thing. Y equals 3 is a horizontal line at 3. Pick any point you want. Doesn't matter where. What's the slope of the tangent line? It's 0. Therefore, the derivative of y equals 3 at any point is 0. This is called the constant rule. So if your function is just a number, like 4, the derivative of it, f prime of x, is always 0. Because the slope of the tangent line for any horizontal line, right, f of x equals 4 is a horizontal line at 4, the slope of that tangent line is always 0. we can go back to the limit definition if you want. Let me do constant rule a little bit better here. The constant rule says that if your function is equal to any constant c, the derivative of that is always equal to 0. Let's do it that way. More generalized than just f of x equals 4. Okay, and we can show that back with our limit definition. The limit as h goes to 0 of f of x plus h minus f of x over h, using f of x equals c, we see that we have the limit as h goes to 0. F of x plus h means I take all the x's and I plug in x plus h. But if I just have a number c, that means there is no x. Therefore, if I plug in x plus h for all the x's, there are no x's, so I still just have c. Minus my original function f of x, which is just c, over h. And that is the limit as h goes to 0 of 0 over h. And I know h is going to 0, but remember, we don't care what happens at 0. It's what happens when we get close to 0, and 0 over some number that's not 0 is always 0. Therefore, the derivative of any constant is always 0. That's our constant rule.